So we will continue from yesterday. We were last time we started talking about the governing equations for inviscid compressible flow. So we will continue from that. Governing equations for inviscid compressible flow, and in fact we already talked about the conservation of mass equation, continuity equation yesterday. So we will continue with the others, and the second one obviously is the conservation of momentum equation. Okay, conservation of momentum. And in the integral form, if we write it in the integral form, by the way, just again, for the sake of argument, just to remind you from yesterday, when we were writing the mass conservation, in reality, we are conserving the mass of a fluid particle enclosed by an invisible boundary. This shape of this boundary can change as the fluid particle moves around, but the mass inside does not change. So written in Lagrangian sense, we just to repeat what we were saying in the last few minutes of yesterday's class, as this particle is moving around, its mass is conserved, and so it's dm dt, the capital dm capital dt is 0, so which is the equation if you follow that fluid particle. But of course, in fluid mechanics, we generally do not do that. We actually use what we call Eulerian approach, and Eulerian approach requires fixing yourselves in space, select a control volume, and through the surfaces of the control volume, watch the incoming quantities. Like if it's mass, watch the incoming mass, outgoing mass from all surfaces, and it has to balance out. So the total incoming versus outgoing balance must be equal to 0. That's continuity equation. We have written it in the integral sense and also in the differential sense yesterday. So the momentum equation is also like that. What we are basically doing is we are applying Newton's law of motion, sigma F equals ma, to this fluid element as it moves around with a certain velocity. So since it has a mass, basically we say that its momentum should be conserved. What does that mean? It means that if its momentum changes while it's moving along, that must be due to some forces acting on it. More than probably one force, so there may be many forces acting on it. So the net force must be responsible for change in momentum. Why? Because this is m times a as we know it, and we can also write it as for a constant mass, and we know that mass is conserved, it's not changing. We know that this is m, I can take it into the derivative, so it is equal to mass times v. So that equation must also be satisfied. Now, when this one is applied to fluid mechanics problem following a single fluid particle, so of course in the fluid mechanics sense, we need to use the substantial derivative of mv must be equal to the total amount of force or net force acting on a fluid particle. Now the thing is, of course, in this form, it's not very useful in terms of fluid mechanics applications. We basically transform this because it's written in Lagrangian sense. We cannot follow every single fluid particle. We transform this into Eulerian approach through Reynolds transport theorem, which I'm not going to do here because that's probably you have seen this in fluid mechanics classes. So when you do that, we obtain what we call the integral form of the momentum equation, and for a given control volume. So you select that control volume in space. That's the volumetric change of momentum. Also, there could be incoming momentum, outgoing momentum from the surfaces. So that of the surfaces of that control volume, that should be taken into account. So ds is basically area, and therefore the unit normal direction of a surface is involved times velocity. So this is this entire thing that I've just written is basically, it corresponds to basically mass times acceleration in short, okay, for a fluid particle written in Lagrangian cells. It corresponds to that. Now, of course, on the right-hand side, we need sigma f. What causes this acceleration, or what causes this momentum change? So many different types of forces can cause that. First of all, basically pressures forces. If pressures are acting on surfaces, this could result in a momentum change. And if there are certain body forces acting on a volume, gravitational forces, or whatever, magnetic forces. So these could be acting on the fluid, so that could change the momentum. And since right now we are dealing with inviscid flow, of course, we do have additional terms due to shear forces, due to the viscous effects, but now I ignored that, so I'm not going to write it on the right-hand side. So in short, for inviscid compressible flow, this is our integral equation for conservation of momentum. So this right-hand side is sigma f, basically. Of course, this is a vector equation, right? So in reality, it represents three different conservation equations for three components of velocity vector. So, and also similar to what we did for the continuity equation, this can also be written in differential form. So basically what we could do is we could change this surface integral to a volume integral through a divergence theorem, and then collect also this surface integral to a volume integral. So everything becomes a volume integral. I'm not doing this because this is very fundamental. I'm not doing it here in this class, but everything turns into a volume integral, which can then be used to obtain the differential form of the equation. For example, for the x component of the momentum, so for the x component of the velocity, let's say u, this will be equal to the pressure gradient along x, so du dt on the left-hand side, the pressure gradient along x plus if there is any x component of the body force. So that will constitute our x component of the momentum conservation equation, x component of momentum conservation equation. Similarly, we can also write the other components. Let's quickly write them. For the y component, the velocity component is v, so minus dp dy plus rho times fy, and we have the z component, which I'm not going to write again in the same equation. So these equations basically represent the law of motion, Newton's law of motion. So sigma f equals ma as applied to a fluid particle. So we have three equations here, and we had one equation from continuity that makes it four. But you know that as our discussion, following our discussion yesterday, we need more equations because our unknowns are more. Of course, the third conservation equation is the conservation of energy, so energy equation. And conservation of energy in reality is basically nothing but the first law of thermodynamics. Okay, so basically as applied to, again, a fluid particle. So if there is a fluid particle moving around with a certain mass, well, it does have, first of all, a certain kinetic energy, right? It does have a kinetic energy, and it should have an internal energy, E, based on its temperature level. And also this, well, if we are dealing with a heavy fluid like water, it will also, the potential energy that it has will also be relevant. But right now, let's consider we are dealing with air flows, so we are not concerned very much about potential energy changes as the fluid particle moves around. So basically, internal energy and kinetic energy level of a fluid particle can change as it moves around in the fluid medium. How can it change? Well, first law of thermodynamics says if there is some heat added to the fluid, or if there is some work done by this fluid element, meaning for whatever reason it may want to expand, it may want to get larger at some point, or it may want to get it may shrink, it may want to get smaller. So due to this interaction with its surrounding fluid particles, basically it can do work. So that could also change its energy level. So in addition, of course, if there are body forces, that those body forces, and if this fluid particle moves in a body force field, that could also invoke some work interaction. So again, so we apply first law of thermodynamics to this kind of interactions that a fluid particle is going through, and when we write it in the integral sense, in terms of after applying Reynolds transport theorem, so in terms of Eulerian approach for the control volume, basically now we say our total energy level of the fluid particle, which in this case is the internal energy plus the kinetic energy for the whole volume, plus for that control volume that we selected, if there is incoming and outgoing energy fluxes, let's say, from the surfaces, so this E plus V square over 2 flux going in or out of the surfaces, basically these two terms represent the energy change that is happening within our control volume. The right-hand side says what actually changes this energy level. And according to first law of thermodynamics, first of all, we could have heat transfer, so acting on the volume. So let's say a Q dot could be acting. So rho times volume. As I said, as the fluid particle is moving around, it could be doing some work. So sorry, not rho, but this must be P. P dot product, I'm sorry, P times V dot product S designates the work done. And if there are any body forces that are acting on the volume and the fluid particle is trying to push them away or getting squeezed because of them, that's also generating some work. So basically that in total constitutes the right-hand side are basically the mechanisms that that affect the fluid particle to change its energy level. Again, on in terms of the differential form, this can be written also in the differential form using same mathematical methodologies that we just described. So it looks more like this. The substantial derivative of the total energy level of a fluid or gas, let's say, so I'm ignoring the potential energy, E plus V square over 2 must be balanced by a heat flux acting on it, a work term that is done by the fluid particles as they're moving, or the work done by the fluid particles as they move against some body force field. So this equation is not a vector equation. Similar to the continuity equation, this is also a scalar equation, which means that it's only one equation. So up to this point, we had 4 equations in our governing equation system. In addition, with the by addition with the energy conservation equation, now that makes it 5 equations. Well, do we have 5 unknowns? No, as we discussed yesterday, we actually have 6 unknowns, because let's remember what those were. So first of all, density, it's a compressible flow, as we discussed. We have to solve for density, and velocity components, let's say UVW, and pressure and temperature. So that makes it So these are velocity components. So that makes 6 unknowns that needs to be solved. And so far we had 5 equations. And in order to close our system, of course, we actually have the ideal gas relation or the equation of state especially for compressible flows where density is not a constant. This is very important. Equation of state. And of course, I just, if you noticed, so this is our fifth equation, I'm sorry, sixth equation, but there's one thing that I forgot to mention. Here in the energy equation, you do not see any temperature, right? Where is temperature? There's no temperature here. There's a temperature related quantity, which is actually E, internal energy. And for a calorically perfect gas, we know that E is actually related to temperature. CV times T, so internal energy. So basically all these equations now, with all these equations, we do have a closed set of equations that govern the motion of a compressible gas, inviscid compressible gas that could be moving around an object, right? And that object is our high-speed flying vehicle in our profession. Good. So after now remembering these equations, there is an important concept in compressible aerodynamics. That concept is called stagnation conditions. Okay. You might have seen this concept in other classes as well. So stagnation, or sometimes we call them total conditions. So we will spend some time on understanding what these are. I mean, when I say conditions, you know, I'm referring to the state of the gas. So state of the gas, as we know by now from previous hours that we spent since last week, the state of a gas is determined by its pressure, temperature, velocity components, density. But related to those parameters, especially relevant to compressible flow problems, we need to define stagnation, what we call as stagnation or total quantities or parameters as well. For example, we need to define stagnation pressure, which is not this P, it is different than this P. So in reality, we use a subscript 0 or subscript T to designate that difference. We need to define a stagnation temperature. We need to define a stagnation density. So we will discuss this for a while. So the one that we know as P, for example, in this list we have P here, right? That P, in reality, we know as let's say a more proper way to name it is, we call it actually static pressure. Okay, static pressure. So it's actually the pressure. Let's say you are a fluid particle and you are just following a streamline around any object. That is the pressure that you feel, okay, on your body. I mean, if other fluid particles are pushing you, or they are pulling your boundary out or pushing your boundary in, this is the one that you feel, okay? So this is the pressure felt when, let's say, traveling along with the fluid, when traveling along with the fluid particles, let's say. This is the actual pressure that you feel. And I mean, you know, when somebody, or for example, in a wind tunnel, if there is some certain airspeed inside the wind tunnel, this is the actual pressure that the walls of the wind tunnel feels, okay, side walls of the wind tunnel feels. Now, but this is not a, in addition to, let me put it this way, in addition to the static pressure, in order to handle compressible flow problems, we also need to define another quantity, which we call stagnation pressure. And we designate it with P0, okay? Stagnation pressure. And stagnation pressure is the pressure at a point in a gas flow where actually velocity becomes zero. I mean, you know that velocity becomes zero at, for example, stagnation points, right? In aerodynamics 1 class, we have seen stagnation points where the flow actually stagnates. You know, stagnant or the word in English, stagnant means not moving, right? Nothing is moving. So stagnation means where fluid is not moving, so therefore velocity is zero, and the pressure level at that point where velocity is zero is called stagnation pressure. Well, there's much more to discuss related to the quantity of stagnation pressure. We will do that in a short while. So this is just kind of a first introductory definition of stagnation pressure. Similar to that, we also define a stagnation temperature, T0, okay? Stagnation temperature, okay? Now, stagnation temperature, there's a formal definition and there's actually a physical meaning to it. It's the value of the temperature of the fluid element if you bring it to rest, meaning that if you take a fluid element, so let's have our fluid element here, it is at a certain temperature, so it does have a certain internal energy level, and it is moving, let's say. And since it's moving, it does also have a kinetic energy level, okay? So and let's say it's moving along this streamline, okay? Now, if you take this fluid particle and force it to go to zero velocity, yeah, so initially it has a certain internal energy related to T, and it has a certain kinetic energy. But now if you take it and slow it down by whatever means necessary, and then it stops, okay, it stops, then so we are doing basically right now what I'm describing is what we call in science a hypothetical experiment, right? It's an imaginary experiment. Somehow some very strong person started to push it back and brought the velocity to be equal to zero. The question is, well, if I did that, I mean, initially it had a certain energy level, right? E plus V squared over 2. Now, and I know energy should be conserved. Now the velocity become equal to zero. Then what will happen to all this energy? I mean, the kinetic energy is zero now. So what should happen, as you might guess now, its internal energy level will increase such that, so because the energy must be conserved, such that the internal energy level at this state, where velocity, or at the stagnation state, where the velocity is equal to zero, must be equal to the total energy level while it was actually moving a few minutes ago. So the temperature that it reaches at this new internal energy level is called stagnation temperature, T0, okay? It is very much important in terms of compressible aerodynamics calculations. We will see why in a short, we will see why in a short while. Now, related to this stagnation temperature quantity, we also define generally a stagnation enthalpy. And for a calorically perfect gas, this is basically Cp times T0, okay? Stagnation enthalpy. We will also come to this very shortly. So the changes that are occurring as fluids are moving at high speeds, or air is moving at high speeds, changes that are related to its state. And by the way, P0 and T0 are two additional state variables in addition to our original list. Original list of other flow parameters. So the thing is, it will be very important for us to understand what happens to these, what we will call now stagnation quantities, as the fluid, gets, experiences certain flow physics as it is moving at high speed around flying vehicles. Those flow physics we will start discussing in a few weeks, like shock waves and everything, expansion waves. But before that, we will now discuss a little bit more to understand these, especially this stagnation enthalpy H0 and stagnation temperature T0. And that is very much, our discussion will very much start from energy equation as we have written it in this class, energy equation. I will write it down again. So rho d dt E plus V square over 2 equal to minus nabla dot product P times V, and I assume I ignored body forces. One thing that I forgot to mention, and it was extremely important. Look, when we were doing this process, meaning that slowing down this fluid particle to zero velocity, to stagnation condition, and the temperature it reaches at that instant will be T0, right? That's how I described it. However, there is a trick to this. We have to be careful, and which I forgot to explain to you. The thing is, I mean, basically, hypothetically, what we are trying to do is to convert its entire energy content into a temperature, into internal energy, basically. But while we are doing this, if somehow we allow this fluid particle, let's say while it's slowing down, okay, we allow this fluid particle to have heat transfer through its boundaries, okay, it will lose some energy. We don't want that. So when we were doing our imaginary experiment, we assume actually heat transfer will be zero, which we call adiabatic process, so that when it reaches to the stagnation condition, it recovers the entire energy level of the original state without losing any of it due to some strange heat transfer happening during the process. So we assume that there is no heat transfer while it's slowing down, so that at the end state we recovered its entire and whole energy level as a temperature increase, so that we truly reach a maximum temperature state, T0, right? So when we come, keeping this in mind, when we come to the energy equation that we're writing, as you see on the right-hand side, there is no heat transfer term, because this process, this imaginary process, is an adiabatic process. Q is equal to 0. And since we are dealing with gases, as I said, I ignored the body, the work done due to body forces term. So this equation represents energy conservation for an adiabatic process, or let's say adiabatic flow, and let's say negligible body forces. Okay. Good. So now we will do some mathematical exercise on this equation. First of all, the material derivative, or also known as the substantial derivative, we know what it is. It's basically equal to the partial derivative of a quantity with respect to time plus v dot nabla operator, v dot gradient operator, right? Now, also, we know that on the right-hand side, we have this dot product, nabla dot p times v, which can be written as p times, because, by the way, you know, what is this reverse strange looking triangle that I've been calling nabla? You know, this is basically gradient vector. So it has three components. First component is ddx, ddy, and ddz. Just as a reminder. So I can rewrite this as p times nabla dot v and plus v times nabla, I'm sorry, v dot product gradient of p. So we can write this derivative using calculus. So basically, so we can write the right-hand side like that, and we can expand the left-hand side like this. In addition to doing this, basically now we will modify the equation such that we will add this term, rho material derivative of p over rho to both to the left-hand side and right-hand side, both to the left-hand side and right-hand side of this energy equation that we have here. So to this equation, okay? And then we start to manipulate the equation a little bit. So what do we have right now? We have the material derivative of our total energy, E plus V square over 2. And now I added this term, rho times d dt of P over rho. Now must be equal to, on the right-hand side, minus gradient dot product PV plus I added this term again, rho dt of P over rho. Okay. Now, obviously, I can, if you look at the left-hand side of this equation, I can group this equation, right? So I can write this is equal to, in reality, rho d dt, now one single term, E plus P over rho plus what? V square over 2. Okay. And well, we have the same thing on the right-hand side. We will deal with the right-hand side in a second, but on the left-hand side, this is what we got. Well, why did I want to? I mean, it may be clear right now why actually I did this strange addition both to the left-hand side and right-hand side is the fact that because I want to see enthalpy on the left-hand side. Because why? E plus P over rho is actually what we call as H enthalpy. Why? Because if you remember from, I guess yesterday we covered it, the definition of enthalpy is E plus P times V. V is the specific volume, and V is 1 over rho, so it's actually P over rho. So this is actually the definition of enthalpy. And yeah, so basically we can, so this is what we have on the left-hand side. So let's, now we will talk about the two terms. We have two terms on the right-hand side. And the first, we will talk about this second term where we have, so let's say also, let's work on the terms on the right-hand side. The first term that I want to investigate is this, the one that we actually added, P over rho, okay? Now, just using simple calculus, this can be written in this way. So rho times, for example, dp dt minus p times d rho dt divided by rho square, if I open up this derivative term. So from here, I have, now I see some interesting terms. first of all, this one, for example, d rho dt, we see the same term in the continuity equation. This is actually equal to, what is it, minus rho times gradient operator dot product velocity vector, okay? This is from continuity equation that we have seen yesterday, differential form of the continuity equation, okay? So, and of course, this rho cancels with this, and you do the cancellations. Basically, what let's see what we got. So rho ddt p over rho now becomes equal to this. Becomes equal to what? First of all, we have the first term dp dt, and the second term minus p over rho, and this is equal to, or actually it's going to be plus, because we know that this is equal to minus rho nabla dot v, so it will be equal to actually rho also cancels because rho is in the coming from the continuity equation, cancels this, so this only becomes p in reality. So plus p times nabla dot v, okay? So this is a better version. This is a better version of this term which we added to the right hand side. So let's use this. We will use this term on the right hand side. So let's do that. We rewrite the energy equation. So we the left hand side, we have this material derivative of now E plus P over rho V square over 2. So that includes the enthalpy as we just discussed. And on the right hand side, we have minus P nabla dot V. And now we have what? Let me see. And actually we have okay, minus p v, so that is correct. I'm just checking if my notes are correct, by the way. So this term, and then open up the material derivative for this. So v dot delta p and plus p dot dv. So as you can see, we have many similar terms that actually cancels out. So basically on the right hand side, we only end up with the time derivative of pressure. Okay, time derivative of pressure. So just to summarize, if I want to write this down, rho ddt of enthalpy plus kinetic energy, v square over 2, becomes equal to dp dt. So now this equation, so again, let me remind you again, this what is this equation after all this simplification? This equation is the energy conservation equation for an adiabatic process with no body forces. Okay, so this is that equation. Why, again, I'm reminding you, why are we interested in this equation? Because this process of slowing down a fluid element to zero velocity adiabatically is governed by this energy equation. Okay, so let's remember again. Good. So if the flow is steady state now, if the flow is steady, this partial derivative of pressure with respect to time, of course, will disappear. So what we will end up with is the left-hand side of rho ddt h plus v square over 2 must be equal to 0 for steady state flow. Okay. So so therefore here basically what we can say in reality is the total derivative, substantial derivative of, I mean, since rho cannot be zero, its density, it will have a finite value different than zero, some number, some numerical number. This term must be zero in order to satisfy this equation. Well, now this equation tells me now another story about the fluid particle that we were talking about. It says whatever this quantity is, I mean, if we are talking about this fluid particle, it does have a mass, it moves around, and we said its mass was conserved. So we wrote that equation, we called it continuity equation. And we wrote other equations regarding this fluid particle as this fluid particle is moving around. But now, for that adiabatic process that we just defined, as we were, for example, slowing down towards going to the stagnation state, is that this quantity of the fluid particle does not change in time as well along a streamline. So if this fluid particle is moving along a streamline towards, let's say I'm slowing it down, this quantity h plus v square over 2 also does not change. Its mass does not change, and also this quantity does not change. So in time, as it's moving along a streamline. So this quantity h plus v square over 2 is basically a constant, okay? And we call this quantity stagnation enthalpy, H0. So therefore, along a streamline, and if, let's say, this fluid particle is moving along a streamline, and it has an initial enthalpy level, let's say H1, an initial kinetic energy level with V1 square over 2. Now, as it moves along a streamline, and if it's an adiabatic process, okay, it could be moving towards slowing down, or it could be going anywhere. I mean, it could be accelerating or decelerating, or of course the extreme case is decelerating, going towards zero velocity. But for any motion of this fluid particle, acceleration, deceleration, its kinetic energy will change. Let's say it reached here to a state 2, but it could be at a different kinetic energy level. One of them could be zero velocity level, a specific case, but it could be at any kinetic energy level for that matter. So V2 square over 2, and it will be at an H2 level. Its enthalpy will change, but their summation will remain constant as long as this happens adiabatically. There is no heat transfer that is occurring. So basically what we are saying is H1 plus V1 square over 2 must be equal to H2 plus V2 square over 2. So H01, so stagnation enthalpy at 1, must be equal to stagnation enthalpy at the second state. This zoom is killing me. Okay, here. Just want to put an equal sign here. So basically, for an adiabatic process, adiabatically moving gas, stagnation enthalpy along a streamline does not change. That's the moral of the story. And stagnation enthalpy, H0, is related to stagnation temperature if it's if Cp is, let's say, a constant for a calorically perfect gas. So which means that along a streamline for an adiabatic process, if there's no heat transfer that is involved, you are not heating up the gas for whatever reason, stagnation temperature also remains constant. Therefore, it's because of that. So for an adiabatic process, meaning Q0, right? Q dot heat flux is 0. Stagnation enthalpy, and therefore stagnation temperature does not change along a streamline. So given a state of the fluid, given meaning the state, meaning a pressure value P1, T1, velocity value V1, or it could be Mach number. We will see later that it's actually Mach number is generally given. We can calculate it's the value of its stagnation enthalpy and stagnation temperature. And if the gas moves to another location, and if that during that motion, if there's no heat transfer interaction that it experienced, it does not experience any heat transfer, its original stagnation enthalpy will remain the same. Its original stagnation temperature will remain the same. So this is kind of an interpretation. This is actually basically the energy conservation equation that in work, okay, energy conservation equation in work. A few things, final points that I would like to make. Let's say we have a bunch of streamlines. This is also a nice plot in Anderson's book, but anyway, I will discuss very fast, and I will repeat this point next week again. Let's say we have a non-adiabatic flow, and we also have same streamlines in an adiabatic flow. So just first, let's compare these. Adiabatic flow. So initially, let's say we have the state of the fluid. Let's say we have an H1 and H01, and we have a T1 and T01 as described, and the fluid moved, or the gas moved along these streamlines. It reached an H02 and H2 state, and similarly T02 and T2. For non-adiabatic flow, which means heat flux is not equal to 0, these are not equal to each other. H02 is not equal to H01, and T02 therefore is not equal to T01, okay? But for an adiabatic flow, as we already discussed, that's not the case. I'm not going to write the same parameters. Let's say we are moving here to here. H02 will be equal to H01, and T02 will be equal to T01 for an adiabatic flow. One more discussion and final point in this hour is that what if in addition to being adiabatic, right, the process is also reversible. Now, adiabatic is one thing, but adiabatic plus reversible process, we call it an isentropic process, okay? So now let's compare same streamlines. So here on the left and on the right, the flow is going from left to right in both cases. Now we will compare non-isentropic flow and isentropic flow on the right, okay? Now, let's start with the isentropic case. Isentropic case involves being adiabatic. So that, first of all, this must be satisfied, right? T02 cannot change. But the reversibility condition impacts actually the other important stagnation quantity, which is the stagnation pressure. So if we have a P1 and P01 at the initial state, and if we have a P2 and P02 at the initial state, reversibility says that there's no dissipative process. There's no entropy generation. So since there's no entropy generation, that actually is directly related into stagnation pressure. How we will discuss next week. But for an isentropic process, P02 also remains constant. Okay, P can change. P1 probably will be different. Static pressure P2 will not be equal to P1, or may not be equal to P1, but stagnation pressure will always remain constant if it's along a streamline, that is, if it's an isentropic process. If it's a non-isentropic process, and that's the left side, it could be adiabatic. It could be adiabatic, but if it's not a reversible process, P02 at the exit will not be the same as P01. In fact, for a real process where you have loss generation, P02 will be less than P01 for stagnation pressures. There is a physical reason to it. We will discuss it next week. Okay. Great. So if you do not have very quick questions, because we are 2 minutes above time, I will stop here after your quick questions if you have any. Otherwise, I will meet you again next week. Any quick questions? No questions? Okay, everyone. So thanks for coming to today's class. Let me stop recording, and I will meet you again next Wednesday. Okay?
İyi günler hocam.